Okay, so quick review from yesterday. When light strikes the Earth's surface, what are the three things that can happen to it? Okay, it could be absorbed, reflected, used. And if it's being used, what process is that? Photosynthesis. Okay, so today we're going to be focusing mostly on what happens to the energy that is absorbed. Okay, because the energy that is absorbed is the energy that can be transferred, okay, around the world and kind of try and even out the energy distribution on Earth. Okay, so that's what we'll be looking at mostly today. And what heat transfer method is going to be most involved in that? Convection. Right, okay, because we're going to be talking about the movement of heat through the atmosphere, which is a fluid. Okay, so we're going to have convection currents, hot air rising, cool air descending. Okay, differences in temperature and pressure. Okay, differences in temperature are differences in energy. That means that the second law of thermodynamics will come into play, and energy will try and move from hot to cold, and convection will occur. And we call convection through the Earth's atmosphere by another name that's much shorter: wind. Okay, so that's what we'll be looking at here. Okay, so we're going to look at how energy is distributed on Earth. Obviously, what part of the Earth gets the most energy? The equator. Okay, but it's not all there. Okay, and some of it gets transferred to higher levels. We talked about that yesterday: convection and latent heat as well. Okay, understand the role that the winds play in distributing energy. We're going to look at the Coriolis Effect. Okay, the Coriolis Effect is an important thing that we need to go over about why winds come from the direction they come from. And we're going to look at global wind patterns as a product of both convection as well as the fact that the Earth is rotating under its atmosphere. Okay, I mean, the atmosphere kind of rotates with the Earth, but there's also a bit of kind of slippage there, right? So the atmosphere could be moving in a different direction than the Earth depending on the wind direction. Okay, so that can always kind of cause changes in direction of the wind. Right, so that's what we'll be looking at today, as well as a few other kind of particular wind mechanisms, especially this one. Okay, the jet stream is also a very important weather or wind mechanism, okay, that moves air masses around, pushes them around. Okay, the location of the jet stream is always a factor when there's going to be a major weather change coming. Okay, as it moves, it pushes air masses around and then causes major changes. All right, so the Earth's atmosphere is always moving. Okay, it's always in perpetual motion. Okay, it's movement that's striving to eradicate the differences in temperature, okay, and energy on different parts of the Earth. Obviously, mostly between the equator and the poles. So there's kind of a natural flow of energy from the equator toward the poles. But while that movement is happening, the Earth is spinning. Okay, so we've got air that's trying to move from the equator north or from the equator south, okay, depending on which hemisphere you're in, okay, but the Earth's always moving as a result. So we get this weird interaction that goes on. Now, the Earth rotates this way, okay, which is why if we're over here, we would be looking to the east to see the sun rise, and then when we get over here, we'd be looking to the west to see the sun set. Everyone kind of follow? Right, so the Earth rotates in that direction. Okay. Now, nature doesn't like imbalance. Okay, the second law of thermodynamics is one of the mechanisms that's used to eradicate that imbalance. Okay, energy flows from hot to cold, but it also can cause air to move because of differences in pressure. There's a high pressure area and a low pressure area. Okay, then air naturally moves from high pressure to low pressure. Okay, and that's usually what causes like the rotation around a hurricane or the rotation around a tornado and things like that. You got a low pressure area and everything's kind of moving towards it. Okay. We typically sense the movement of air, obviously, as wind. And is wind, is it able to do work? Yeah. Okay. We want to be able to harness that. Okay. Wind is an energy mechanism. Okay, that we could use to convert into other forms of energy. Right. Obviously, you know, we've got the wind farms down there at Pincher Creek. There's also some out by Carbon to the east. Okay, where they've got the big windmills. Okay, that are generating electricity. Now, do they generate a lot of electricity? No, they don't. It's nice because it's pretty green. Okay, like I mean, there's not a lot of pollutants and stuff that come from that, but there's a lot of moving parts there, and also they kill birds. Like apparently quite a few because some people made a big stink about it. Like first they were like, oh, stop using carbon and coal and whatever, so build these windmills, and then it's, well, these windmills kill birds. Well, you can't have it both ways. Okay, you know, if a bird's dumb enough to fly into the propeller, Maybe that's natural selection. I don't know, but yeah, they are good. They do generate a fair amount of electricity for as big as they are, and obviously they don't have a really big carbon footprint. Okay, so that's a positive. Definitely, if we can use more wind, that's awesome. What's the problem other than that they kill birds? It's not consistent. If it isn't windy, they're not making any electricity. Okay, that's why they're generally around like Pincher Creek and Carbon. Those are places where it's pretty consistently windy. Okay, what's the other problem with them? Yeah, they're expensive initially, but maintaining wise, they're not too bad. Yeah, they're loud. Nobody wants them in their backyard because they hum when they're going. They make actually quite a bit of noise. It's like an airplane propeller, except way bigger. Okay, so the thing's whizzing around, and it actually makes a fair amount of noise. So, yeah, people don't want a wind farm right next to them. But I mean, people don't want a coal plant right behind them or a nuclear power plant on their doorstep, or stuff like that. So it's hard to always make those kinds of things work. All right, so distributing the Earth's energy budget. Okay, we'll talk about the jet stream first. Okay, so the jet stream is a major wind mechanism, but it's very high altitude. We talked about yesterday, it's in the stratosphere, right? That's 30 kilometers or higher up into the atmosphere. Okay, sorry, 10 kilometers or higher up into the atmosphere. So we've got very, very high altitude wind, but it moves very, very fast. And as a result, it can push other air masses around as it moves. Okay? So the jet stream is what weather our meteorologists always watch, okay, when they're trying to predict weather over the next, let's say, like week or so. All right. I mean, if you've ever looked at like the long-term forecast, okay, they're only really good at predicting how wrong they'll be after about 5 days. Okay, their reliability after about 5 days is pretty low. Okay, but usually you can predict 5 to 7 days fairly reliably. And what the major way that they do that is they look at the location and movement of the jet stream. Okay, location and movement of the jet stream will tell them where air masses are going to come from. So this is a kind of a summer pattern, okay, but it's unusual, okay, but it's a summer pattern that we saw a few years ago. So we got the jet stream here coming off of the Pacific Ocean, okay, kind of, not really far north on the Pacific Ocean, but northerly. So that was bringing in this warm, dry air, but it kind of trapped it in this area. And this area was normally a low pressure area, but it had trapped a high pressure area right here, okay. Now, around that high pressure area, the jet stream got turned, okay, because in a high pressure area, you have rotation that's kind of like clockwise, okay? So it pushed around there, and as a result of it pushing around, it started pulling cold air from the Arctic down between these two high pressure areas. This cold air couldn't move to the east because there was a high pressure area here. It couldn't move to the west because there was one here, and the jet stream pulled it down into the prairies, essentially. Right? So as it moved down in there, okay, it also, the jet stream got turned and went back out into the ocean where it picked up a bunch of warm, moist air and then turned and brought it back over the central United States. Now, what is this area called? That's Tornado Alley. And this pattern arises, okay, a few times a year through Tornado Alley and leads to, okay, you've got all this cold air meeting all this warm air, and you get really unsettled weather where you get thunderstorms. You get that thunderstorm cycle, right, where in the morning it's nice, and in the afternoon it builds, and then you get a storm in the evening, and then the next day the same thing happens, just kind of goes for a while. Okay, so that's kind of what the jet stream can do. The movement of the jet stream will influence where air masses move to, and so that's what meteorologists watch. Okay, if the jet stream is doing this, they know it's going to be bringing some cold air in, and that we're going to get a kind of colder weather, clearer weather. Okay, as long as there's not another belly to this thing that's going to bring more moist air up from below to meet it. Okay, in a case like that, we would also have kind of unsettled weather, okay, in this area as a result of that. Right, so everyone kind of follow on that. So the jet stream really moves things around, but it always generally moves from, I shouldn't say always and generally, it always blows from west to east where we are. Okay, it moves all over the place. It's very serpentine, but it's always west east, okay, in general, right? Because it's going to have some north south jogs to it, but it always goes that way in our part of the world. Okay. Over a few days, the jet stream will only usually, it moves, its shape changes slowly. Okay, that's what the meteorologists watch, is they watch the changes in the shape of the jet stream, because that tells them what kind of air it's going to be pulling and pushing. All right, so it really does help to bring different types of air. So if it, if it dips down into here, it could be bringing pretty warm, moist air into an area that would otherwise be cold, or the exact opposite. It's bringing chilly air and forcing it down into an area that's normally warm. Okay, so it does transfer a lot of energy in that way, just by moving air masses around. All right. There's a northern hemisphere one. The one in the southern hemisphere works differently because there's less continental mass. A lot of it is also influenced by kind of landforms, and that land heats up differently than water does. There's far more ocean in the southern hemisphere than in the northern hemisphere. Okay, everyone with me on what the jet stream is? Okay, so basically wind mechanism that can transfer energy from northerly climate or northerly areas to southerly, or vice versa. All right, now prevailing winds. Here, our prevailing winds generally come from the southwest. Okay, the reason for that is what I'm about to show you. Right, at the equator is where we get the bulk of the solar energy. Okay, so that's where the atmosphere is going to naturally have the most energy and be kind of the warmest. Okay, so at the equator, that hot air is going to rise. Okay, it's going to go up, and air is going to move in from the north to replace it. So what we see here in these things that are called Hadley cells, these Hadley cells are really just a convection current. Okay, so hot air will rise, and then there'll be other air that'll move in to replace it. Obviously, air can't just rise and not be replaced, otherwise it would create a vacuum, okay, and that doesn't happen. So air moves down from the north towards the equator in order to kind of take the place of this air that is moved. Right? This other air that's moved upwards will start to cool, but will move northwards because it's kind of being pushed that way by the current that's being formed. Okay? When it gets to kind of the mid latitudes, okay, then it kind of ducks under. Okay, and starts to move north because it's warmer than the air that's presently here. Okay, so it's going to duck under and move upwards. The cold air aloft also tends to move upwards just because there's a lot of pushing force coming from this. You can see how this Hadley cell here is kind of wedged under this one, and it creates a real pushing force here. Okay, so you've got air that's moving northward here. Everyone follow me on that? Okay, we're at the very top of this part of this air movement, okay, which is why we typically get southwesterly winds. So the Earth is rotating this way. Air is trying to move from south to north where we are, but we're moving into it as it does so. Okay, so as the air moves north, we're rotating into it, which makes it appear to deflect and come from the southwest instead of directly from the south. All right, everybody okay with that? All right. Now, typically, okay, we get kind of unsettled weather, right? We have that expression in Alberta that if you don't like the weather, wait 5 minutes. Okay, and that's because we are kind of right here on the border between what are called the mid-latitude westerlies and the polar easterlies. Okay, we know we get wind out of the northeast, it's going to be all bad real soon. Okay, because what's the only thing that wind from the northeast can bring? Cold air, right? Okay, so it's going to bring that cold air in. So sometimes, like these latitude lines here where these Hadley cells are, they're not like borders of a country. Okay, they're not fixed. They fluctuate. They move up and down all the time. Okay, so we can kind of see the effects of that where we live. Sometimes, most of the time, we get it prevailing from this direction, but once in a while, we get a wind from the other way. Okay, everybody kind of with me on that? Okay, so this is convection going on and causing the prevailing winds because the Earth is rotating underneath this north-south moving air. Because really, the atmosphere only moves north-south, okay, in terms of distributing energy. But because the Earth spins under it at the same time, it deflects it. There's cold air on the top and warm air on the bottom, okay, just because of this wedging effect. Okay, everything is really getting pushed towards our area. Okay, we always get sandwiched in the middle. Right? We got wind coming down from the north. We got wind coming up from the south. It just kind of meets in the middle here. Okay? That's why, again, this area tends to lend itself more to inconsistent weather. Right? Okay, so maybe it's a little clearer to see it here, right? Like you can see the hot air rising here, okay, and then going aloft and wedging underneath. Now, I know it looks like it changed from cold to hot. It's just a matter of comparison. This air, while cold for the equator, is warm for mid-latitude. Okay, so it wedges underneath. Okay, and you generally just get a movement toward the north here. Well, it actually circulates. Remember, you guys heard here last when we got it really cold about the polar vortex? Okay, you guys never heard polar vortex? When we get a really bad cold snap, they always talk about the polar vortex. Well, the polar vortex is because at the pole you get this. Okay, that's what causes the easterly winds to come down from the pole. It rotates. There's almost like a, well, it's a vortex. It's a turning wind at the top that just rotates that direction. Okay. In fact, all planets that have observable atmospheres have a polar vortex. Okay. On Saturn, it's actually shaped like a hexagon. Okay? It's like really unusual. It's almost a perfect hexagon when you see the top of Saturn. Okay. But all planets that have a thick atmosphere have this polar vortex. All right, everybody okay with those ideas? So we got convection going on, Earth rotating underneath it. Now, this deflection of the winds is what we call the Coriolis effect. Okay, Coriolis effect is the turning of a wind because of the rotation underneath. Now, let me get this demo here. It's a little bit ghetto, but near the equator, this deflection is almost total. Okay, like the winds are very easterly. So this is actually something that back in, like, let's say, 1500s, 1600s was a really important transport mechanism. Okay, that's why these are called the trade winds. In order to get to the New World, the Europeans would have to sail down past like Spain and Portugal and places like that, okay, to catch these easterly winds that would blow them towards the New World. Okay, and then they would sail up the coast, catch the westerlies, do all their trading, and then sail back to Europe with the westerly winds. Okay, you couldn't sail back to the east using a sailing ship, okay, at the equator because the wind doesn't blow the right direction. Deflected. Does it say reflected? No, deflected. Deflection means to turn it by pushing on it, right? Like if someone takes in hockey, if someone takes a shot at the goaltender, but someone's standing in front and they hit it with their stick, that's a deflection, right? They change the direction the puck is traveling by exerting a force on it. To reflect it would mean to send it back, okay? Which they probably wouldn't do. Yeah? The Coriolis effect is the deflection of these winds because the Earth is moving under moving air. The Earth rotates under moving air, producing a perceived change in direction. The winds aren't really doing, like the air isn't really doing this. We just perceive it to be doing that. Okay? It would be like if you stuck your head out the window of a moving car. You won't do that because it's not safe to do. Okay? But it would feel windy, right? Even though it isn't windy, you're just moving through the air at a high rate of speed. Well, that's essentially what we're doing here. The air is trying to move north-south, but we're moving through it from west to east. Yeah? Yeah, the air is moving north-south, but because the Earth is moving under it, it makes it seem like it's doing that, right? And so we get that movement of air to appear that way. Okay, so that's kind of the Coriolis effect here, which is kind of the next thing we're going to talk about. Actually, I got ahead of myself, but okay, all of these convection currents, okay, we've got 3 of them in each hemisphere on Earth. Okay, the bigger the planet is, the more bands of these you would have. Okay, Earth is only so big, so we've got a big one, kind of from the equator to the horse latitudes, and then we've got a kind of a smaller one, and then the polar vortex at each pole. Okay, everybody with me on that? In the middle, they're actually doing the same thing. They're just coming. One's coming from the north, one's coming from the south. They're turning. Okay, so they're both turning like this. It just means that near the equator, it always feels like the wind is coming from an easterly direction generally. Okay, if you're below the equator, it would feel generally southeast. If you're from the north, if you're north of the equator, from the northeast. Okay, so yeah, we get the trade winds. Okay, these are the trade winds through here. Okay, and then you get the westerlies kind of through here, and then you get the polar easterlies up here, right? And that's all caused by the rotation of the Earth under convection currents. The South Pole would be called the westerlies. Well, no, they would still be easterlies in the south. They would just be coming from the south instead of from the north. Yeah. All right. But yeah, so the Coriolis effect just causes these kind of weird rotations. It does not, however, and if anyone's ever heard this, cause toilets to turn the other way. Okay. There's like this big myth for a long time that in the southern hemisphere, when you flush the toilet, it went this way instead of this way because of the Coriolis effect, which is totally not true. Okay. Toilets just flush. Yeah. Okay. Yeah. Definitely not true. Yeah. No, no, I'm saying it's a calm day and I'm driving and I stick my head out the window. Mhm. Okay, is it blowing? Are you driving into the wind or with the wind? Okay, if you're driving into the wind and you're going this way, it would feel like the wind's going 60 because you're moving into a 30 km/h wind at 30 km/h the other direction. It would make it feel stronger. Okay, it would feel calm if I went 30 km/h and I had a tailwind at 30 km/h. Then I wouldn't feel it. Okay, it feels stronger to go into a wind than it does to go with the wind. Okay, just imagine you're outside and you're walking into the wind, right? That's harder than turning around and going this way, right? Okay, walking with the wind. You don't feel the wind as much if you walk with it, right? It's differential. Okay, it's this. If I have a 30 km/h wind south and I move into it at 30 km/h north, the difference is 60, right? It feels bigger to me, right? All right. Any other questions on that one? Okay, so Coriolis effect and prevailing winds go together. So if there's any questions about prevailing winds, you probably want to talk about convection. I should probably write this down. Okay. If there's any questions about prevailing winds, okay, the things that are interacting are convection. Okay, that's these. You might even want to draw that picture or something, or maybe I give you that picture. Okay, you want to talk about convection. You want to talk about the Coriolis effect. Okay, those two things interacting are what cause prevailing winds. So you got energy differences. Okay, hot air rises, cool air descends. That's convection. Okay, the Earth rotates under these cycling patterns of air. Okay, and that causes a perceived deflection of the air. All right, so remember how I was saying on Earth we got 3 bands in each hemisphere? Okay, there's even more on Jupiter because Jupiter's way bigger. Okay, and you can actually see this kind of striping effect. Okay, on Jupiter, you can actually see the striping effect of those different layers because it's made of hydrogen, it's got different colors, whereas our atmosphere is transparent. Okay, unless there's clouds to watch move, you can't really see the movement of our atmosphere. Well, Jupiter's always got clouds, so you can really see how these winds actually go opposite directions. I'm going to show you a video here in just a sec where you can actually see the cloud tops on Jupiter going opposite directions right past each other, okay, because of this same effect. The red spot is actually an anticyclone. It's a big hurricane, okay? And it's been going for years and years and years. It is shrinking. Yeah. So there's other ones too. Like when you look on like all these little white spots, okay? Those are also big storms. Okay? Like some of these little white spots are like the size of Earth. Okay, you could fit 2.5 Earths across the red spot. Okay, it's just a giant pressure differential there. Okay, but you can actually see that the winds blowing on one side of it are going like this, and the winds on the other side are going like this as it circulates. I may have drawn that backwards, but you get the idea. Okay, so it's circulating, and the winds just keep driving it, right? They keep causing this rotation to happen because the winds on either side of the storm are going opposite directions. The jet stream and the Coriolis effect don't relate. Okay, the jet stream is what causes changes in the weather to happen. If there was no jet stream, we'd always get winds from the same direction. The weather would always be the same. Nothing would ever happen. But because the jet stream can cause changes in that and force air masses to go where they wouldn't normally, then we get those changes in weather. No one's really sure on that one. But they just know that over time it's shrinking. I mean, all storms eventually have to end. So just that one's been around for a long time. It's kind of been the characteristic of that planet for as long as we've known it was there. Okay, any other questions? Okay, I'm gonna show you that quick video here. All right, so you can see there that there's often, because Jupiter's atmosphere is much different in color and composition, we can actually see those different bands working, okay, on there. Okay, and the other part of that is that, like they said, it spins way faster, right? Jupiter's way bigger than Earth, yet it takes only 12 hours to make one complete revolution. So a day on Jupiter is only 12 hours long, okay, whereas on Earth it's 24. So it's spinning faster, it's got way more gases, it's way bigger, okay? That contributes to there being more layers and more bands in its atmosphere. Okay, so the Coriolis effect, we kind of already talked about that. This was kind of the diagram of the basketball demo I did. Okay, where if something is trying to move in a straight line from here to there, but the Earth is rotating underneath it, it's going to do this. It's not going to move in a straight line. It's going to get deflected, and it's going to end up over here instead. Okay, so it's going to be deflected, okay, towards the west, okay, when moving from north to south. If it's moving from south to north, it's going to get deflected to the east. Now, remember, winds are named by the direction they come from, not the direction they go to, okay? So a wind that blows to the east is actually a westerly, okay? And one that blows to the west is actually an easterly. I don't remember. It was the wind speed that was 300, I think, yeah. For a plane? Typically, no. A plane just, I mean, yes, the Earth is rotating, but planes I guess they kind of account for that, but it's not something they really have to worry too much about. I mean, I suppose a little bit, right? I mean, you're flying through the atmosphere. It's not like driving a car, right? You don't have to worry about driving off the road because the Earth is rotating when you're driving a car. Okay, but it probably is something you have to account for a little bit, okay, with a plane. Okay, everybody all right with that? How that Coriolis effect thing works? Okay. All right, so just definition there, the Coriolis effect is that deflection of any object. It's actually an apparent deflection of any object from a straight path by the rotation of the Earth. Okay. All right. Okay, I want you guys to write down some answers for those questions. Give you a couple minutes and then we'll go over them. Then I'm going to move on to specific heat capacity. Okay, so first question. If there's unequal distribution of solar energy on Earth, that's going to cause what? Thinking of two words here. Okay, it might cause that. Wasn't what I was thinking of, but yeah, it could cause unequal air pressure. Okay, jet stream maybe a little bit. Convection, yeah, that was the one I was looking for. It's going to cause convection, right? We know the second law of thermodynamics says if the energy is not equal, it's going to try and transfer it to the place that's lower from the place that's higher, okay? And convection through the Earth's atmosphere is known as a much shorter word, wind, okay? That's what I was looking for, that question, just convection / wind, okay, is what's going to be the result of that. Okay, Coriolis effect influences the direction of winds in the northern hemisphere because as the air in the atmosphere tries to circulate in a convection current, the Earth rotates under it, making it appear to be deflected. Okay, in other words, if you're near the equator, it appears to come from the northeast. If you are in the mid latitudes, it appears to come from the southwest, and if you're at the higher latitudes, from the northeast. Okay, because the Earth is rotating under rotating air. Okay, just the rotating air is rotating vertically. Okay, that is a north-south direction. Okay, and the Earth is rotating horizontally. Okay, that is from a west-east direction. All right. Okay. What are the trade winds? What kind of winds are they? They come from the east. Yeah, the trade winds are easterlies. They blow towards the west from the east, so they are easterlies. Okay. So they're easterly winds that are kind of between the mid-latitudes and the equator. Right? They're called the trade winds because that's what traders back in the sailing ship days used to use in order to get to the New World. Okay, and jet streams are, David? Okay, so yeah, it's not the jet stream's not an air mass itself. It's a wind mechanism that pushes the air masses around. Yes. Okay, so it's a wind mechanism. A high altitude wind mechanism would probably be something you'd want to include in that. Okay, that can move air masses around, kind of contrary to the prevailing winds. Okay, and Coriolis effect and stuff like that. Air masses. Okay, so like when we get the polar vortex, it's that can usually be the jet stream pulling that further down. Okay, causing that cold air mass from the north to move down into our area before it shifts and pushes it back up. Jet stream is a wind mechanism that can move air masses around, causing changes in weather. Right? If there was no jet stream, we would just constantly have the same weather, which, if it was nice, would be fine. But if it was crappy, would be not so good. All right, any other questions on those?